Hello friends, welcome to Susan and John MathTube. I hope all of you are having a good time, and I'm back with another topic, and that is our derivative. The derivative is a part of the subject called calculus. Of course, it's a part of mathematics, and calculus is a subject which changed the way even human beings were living, and it was found in the 1600s, and two mathematicians, Sir Isaac Newton and Leibniz, are credited for calculus. And today we'll be discussing only about the meaning of derivative. I come across a lot of students who are very good in differentiation techniques. Many of them know product rule, quotient rule, and all the techniques, but I have heard many students asking, sin x, when I differentiate, it becomes cos x. But I really don't understand what it means. Or some of you may be wondering, the derivative of x square is 2x, but you're not able to figure out what exactly this implies. So in today's video, we'll be discussing only those things. Okay, let's start. But before we start, you should be good with functions. Now look at this. We have many real life patterns around us. For example, if you take a hot cup of coffee and put it near you, you'll feel that the heat is coming towards you. Or we can imagine patterns like arrowheads moving towards you. Okay, I have my coffee. So it's like heat moving in pattern. Or we have our day, night, that is another pattern. Or if you go to an open ground and you throw a stone with a slight inclination, it is going to move, or it is going to take a parabolic path. So what I am trying to convince you is, we are surrounded by many patterns, and these patterns can be modeled into mathematics using functions. Or function is one of the basic tools which helps us model real life patterns into mathematics. And we write functions with the help of variables. For example, if you have a function in one variable, we will write y is equal to f of x. F stands for the rule. I'll give you an example, x square. So the rule here is you're supposed to square everything. So you input any number, the output will be squared. Or you can imagine another function, the trigonometric function sin x. So you input angles and you get sine of that angle. So basically the function is an input-output device. Okay, so moving ahead, let's say we have a function in one variable y equal to f of x. I'll make things more clear. We have real life patterns, and real life patterns can be modeled into mathematics using variables with the help of functions. And today I'm going to take a look at function in one variable. My function will use only one variable. Okay, now the second thing. Functions can be converted into graph. Let's take an example. Let's take that x square again. So we have a function, the squaring function. And let's say I'm going to input all the possible real numbers. I can input 5, I can input 10, I can input 25, I can input whatever I wish. Okay, now to plot the graph of x square, I'm going to input a few numbers which will be easy to plot. If I input 0, the output will be 0 square, and I get a coordinate 0, 0. And if I input 1, I get 1 squared as the output, and that gives me another coordinate 1 comma 1. And if I input 2, I get 4 because 2 square is 4. Similarly, if I input minus 1, I get 1, and if I input minus 2, I get 4. And I can input any number in between 1 and 2, like 1.5, 1.33, etc. I don't know those squares, but look at this. Corresponding to every input, I get the output as x square. Okay, now let's plot it. So we have 0, 0 here, and then what you call 1 comma 1 over here, and 2 comma 4 maybe somewhere here, and in between there are many values, and that gives me a parabola. And on the negative side also the same thing happens. Minus 1 square is 1 and minus 2 square is 4, etc, etc. So we get a parabola. Okay, now similarly, if you draw the graph of y is equal to sine x, you will get something like this, because sine 0, 0, 90, etc. So look at this. Once more, I'll stick to the point. We have real life patterns, and real life patterns can be made into a mathematical model with the help of variables, and we call them functions. And today we are discussing derivative, and for that purpose I'm going to consider a function in one variable. Every function corresponds to a graph. The input will be x and the output will be f of x. Okay, so if you have a function y equal to f of x, we can expect something like this. And if this is a, this height is going to be f of a, so that this point will be recognized as a comma f of a. If this is b, then the output will be f of b, so this point will be b comma f of b. We learned that functions have graph, and you can see that some functions are increasing and sometimes they are decreasing, and again they are increasing, or maybe sometimes there are functions which are only decreasing, or maybe functions which are only increasing. Okay, so we are always interested in these things, because I told you our real life patterns are changed into functions, and once we convert function into a graph, we are able to analyze this real life situation. We can see that this part is increasing, and then at a certain point, let's imagine we are analyzing the profit of an industry. You can imagine the gold market or the share market or anything. Let's say this is time, and here we analyze the profit. So if it goes like this, we can say that we are making more profit with time, and maybe after some time it may start to decrease. Recently, if you look at the price of gold, it went very high and then it started coming down. Maybe after some time it may go up again. So look at this. This graph actually talks about the function, but the function talks about our real life scenario. So basically this graph is connected with this scenario. But practically plotting graphs are not that easy. I'll repeat, we have very powerful tools today, even today, but plotting graphs are not feasible. Maybe you'll be thinking it's easy to plot graphs in one variable. Okay, maybe with the help of technology it may be like that. But remember, this science, this calculus was found 400 years back. And at that time, plotting was really difficult. Okay, leave it. Even today, suppose you have a function in two variables, let's say something like this. And I think you noticed one thing. When you have a function in one variable, it takes two axes to plot the graph. I'll repeat, when you have a function in one variable, we used two dimensions to plot the graph. So if you want to plot a function in two variables, we must have three axes. So look at this. Even today, graphing is not that easy. And if you have a function in three variables, it ends up in fourth dimension, and I don't know how to plot that. You're not going to. Maybe after some years, we'll be able to visualize those things very easily. But with today's technology, it's not that easy to visualize these things. So we need an alternative method. We need an alternative method where we can visualize the increase, the decrease, and the maximum points, the minimum points, and the bend in the graph. All these things. And that is exactly given by our derivative. I'll repeat once more. We had our real life scenarios which are converted into functions. And for today's example, I'll be using only a one variable function. And you saw that one variable function can be changed into graph by plotting x and f of x in the two dimension. And once you have a graph, you're able to visualize the increase and decrease in the function, which shows the increase and decrease or the real life implications of the graph. But now we are in big trouble because I just told you graphing is not a feasible method. But 400 years back, Sir Isaac Newton and let's say our Leibniz, actually Newton started from derivative point of view and Leibniz started from the other side. They found an amazing method which will eliminate the use of graphs. But still, we will be able to predict whether the function is increasing, decreasing, the maximum points, etc. Okay, so point number one. Let's take a look at an increasing function. Now, if I try to plot the tangent, you can see that the function keeps on increasing. So if you try, it's a challenge. You can do this. You can take a sheet of paper and a pen and a ruler and try this. If you plot a tangent at any increasing part of the graph, if you draw the tangent at any increasing part of the graph, I'll guarantee one thing, the inclination will be acute. You try it, you take any increasing graph and try to plot the tangent. The inclination means you have to take the angle from x-axis to the line. You have to take the angle from x-axis to the line. That will be acute. At the same time, if you have a decreasing function, let's say something like this, you try to plot the tangent, the inclination will be more than 90 degree. This is our 90 degree mark. Okay, so inclination will be obtuse. Okay, now one more very interesting thing. Suppose we have a graph like this. You can observe one thing. At the maximum point and at the minimum point, at the maximum point and the minimum point, the tangents will be parallel to the x-axis. At the maximum point and the minimum point, the tangents will be parallel to the x-axis. Okay, so we observed three things. In increasing function, the tangent makes acute angle. In the decreasing part, the tangent makes obtuse angle, and at maximum and minimum points, the tangents are parallel to the x-axis. Now look at this. You have learned a concept called slope of a line. And always remember, this tangent is a line. Okay, slope is nothing but tan of the inclination and is denoted by the letter m. Now look at this. If inclination is equal to 0, then tan theta will be 0, so slope will be 0. That means at the maximum point and the minimum point, the slope of tangent will be 0. Now, if the inclination is less than 90 degree but more than 0, then slope will be positive, because slope is tan theta, and you can imagine tangent of any number between 0 and 90, it will be positive. And that implies if you have an increasing function, then the slope of the tangent at any point will be positive. And if theta is equal to 90 degrees, then the slope of the line will be infinity. It will be infinity. That means if the tangent is parallel to the y-axis, we are going to get slope as infinity. And if theta is more than 90 but less than 180, what happens? The graph will be decreasing and the tangent will be making obtuse. Obtuse means more than 90 degree, and the slope will be negative. So I'll make things more clear. We started with real life scenarios, and real life scenarios were changed into functions. And we learned that functions can be changed into graph where every coordinate will be given by x comma f of x. Of course, graphical method is very nice, but sadly, graphical method is not always feasible. So we are looking for an alternative. The alternative is nothing but slope of tangent, because the tangent can decide whether a function is increasing or decreasing, or whether the function is at a maximum point or minimum point. If you ask me how, it's very easy. The tangent is a line. You measure the slope of that line, and if it is equal to 0, then we can understand the tangent is at a maximum point or minimum point. If the slope is positive, then we can understand the tangent is at an increasing part of the graph. And if the slope is negative, then we can understand the tangent is at the decreasing part of the graph. And if the slope tends to infinity, we can understand the tangent is parallel to the y-axis. You might be wondering why I'm talking about tangents. Okay, my friends, that is exactly what derivative means. So remember, derivative or dy by dx which you find is nothing but slope of tangent to the function y equal to f of x at any desired point. Okay, right now I'm going to stop this video, but in the next video I'll give you a clear cut idea and the derivation how dy by dx becomes the slope of tangent, and we'll be learning about first principles. I'll repeat once more. So what we learned today is real life scenarios can be changed into functions, and functions can be changed into graph. Graphical method is very good because it helps us visualize the function. But graphical method is not always feasible. So we want an alternative, and that alternative is dy by dx, or our derivative. And derivative is nothing but slope of the tangent of the graph at any point. So I'll be back with the next video in which I'll give you the proof how dy by dx is the slope of tangent. If you like this video, please share with your friends and subscribe and like. So we'll meet soon. So till then, bye from Susan and John.